Hey guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to be taking a look at the RTX 3080 Founders Edition PCB from NVIDIA. And as of right now, this is one of the nicer PCBs you can get your RTX 3080 with, because there is a reference PCB design that can be configured to actually be a nice, solid, PCB. However, it is an extremely flexible PCB design, and so everybody using it has basically configured it for maximizing profit margins. In other words, they've cut every single corner that they could while still producing a functional GPU. Now, with the Founders Edition, NVIDIA hasn't done that.
Before that, this video is brought to you by the Gigabyte Z490 Extreme motherboard. The Gigabyte Z490 Extreme motherboard is a high-end overclocking board built to Gigabyte's highest quality standard and tuned for memory overclocking, CPU overclocking, and system stability. The Z490 Extreme runs a densely finned heatsink for its VRMs, has RGB LEDs for flare, and uses 90-degree connectors everywhere it can to improve cable management access. Learn more at the link in the description below.
We have quite a lot of nice parts, though there is still some cost optimization going on. This right here is like $4 worth of parts that I really don't see why they had to leave out. Also, before anybody asks, no, you can't put the memory chips back on. The memory controllers should be disabled in the silicon itself. So even if you put the two memory chips back on, the GPU shouldn't be able to talk to them. And the BIOS probably wouldn't allow you to talk to them either. So yeah, just don't think about it. Like we've been seeing cards with missing memory chips for a long time. You can't put the memory chips back on. It would be really stupid of NVIDIA to allow that. It is worth noting that in the future we will be seeing, like full custom PCBs from the various board partners that are definitely going to be significantly better than this and going to come with higher power limits than this, and just all around better in every single way, shape, and form. But for now, this is definitely not the worst PCB that you could get your hands on because, well, we have all of the downcosted AIB reference cards for that. So let's get into it. Now, the power delivery on basically all of the 30 series cards is a bit of a mess in terms of how it's laid out. And there's a very good reason for why it's laid out like a mess, but it is just kind of hard to, highlight because of that. So what we've got going on here in terms of power delivery is I'm not drawing out phases here. I'm actually drawing out the splits in the power, like in terms of the VRMs. So we've got three main power rails on these. We've got Vcore. We've got what I like to call Uncore voltage, so V Uncore. Which is basically memory-related stuff in the GPU core. So not the actual CUDA cores or the RT cores, or at least I don't think the RT cores are part of that. But it does include like memory controllers, some of the caches, maybe all of the caches. I'm not entirely sure. I don't have exact details on that. But there's a second like core power rail that doesn't actually power the main cores. And then of course we have memory power. So VMem. Now, how this is scattered around the board is like these three individual phases are the VMem. So we've got VMem over here, we've got VMem over there, and we've also got memory power down here. And so that's a three-phase, and the reason why the memory VRM is configured like this is it improves power distribution between the memory chips, because in the past, GPUs would basically stick their memory VRM like here, or all of it right here, or sometimes behind the Vcore VRM, which was like, yeah, we really want to lose power through the power plane. Now, the problem with doing that, but like for the sake of simplicity, let's imagine that the memory VRM was entirely located up here. Now, the problem you run into with doing this is that all of the memory chips are specified to run at 1.35 volts, but not all of them are right at the actual memory VRM. And so if the memory chips pull a significant enough amount of current over a low enough cross-section power plane, you basically end up with potentially a very significant amount of voltage drop. And what that translates to is that, if we want to feed this memory chip over here with 1.35 volts, but our VRM is over there, we might need to be outputting 1.4 volts here so that by the time the current gets to this memory chip over here through the resistance of the power plane, it still is at 1.35 volts. Now, the problem is we do have a bunch of memory chips right next to the memory VRM, and so those are getting overvolted. Like, those are just straight up overvolted by like 50 millivolts. This memory chip might be overvolted by like 40 millivolts. It might be at 1.39, then the next one down 1.38, right? So you get basically like a high spot of voltage over here, and then going around the PCB, the voltage steadily decreases until you get to the furthest point away from the VRM. So that's not ideal for power distribution. Also, that voltage drop is actually just straight up lost as heat in the PCB. So those 50 millivolts, they don't just magically disappear. That's 50 millivolts of heat just being dumped into the power plane, or more like being produced by the power plane due to the resistance of the power plane. So one of the workarounds for this is, you make a thicker power plane, but that can get very expensive and not real, like, potentially isn't really a viable option depending on just how much current you need to handle. And so the solution that NVIDIA has here is just put a little bit of memory VRM everywhere, so that like these memory chips pull most of their current from here, and so the voltage outputted by this phase over here doesn't need to be significantly higher than what the voltage that the memory chips actually demand, because the current doesn't have to travel a very large distance. Same goes for the memory chips down here and the memory chips up here. And then, of course, if you had a RTX 3090, they would also populate this memory VRM up here, and then these chips would be getting, some of their power like this. That's the idea behind the scattered memory VRM. It just helps with power distribution to all of the memory chips. We were looking at a similar situation with the Vcore and the Uncore rails, where this strip right here is all Vcore. So all of this is Vcore, and then all of this is Vcore. And so the idea with this, again, is that basically if we're pushing current into the GPU core from both sides, we get reduced power losses, because effectively the cross-section of the PCB is now something like this at its skinniest point, right? You have these two sections coming into the GPU core, instead of what you would normally get with a regular GPU, where you might have something that looks sort of like that. The funny thing is, like, with the Vcore, it's not even so much the power plane cross-section as it is, like, if you have a really high current draw GPU, like, say, a Vega, you actually get a noticeable voltage difference just measuring the voltage behind the GPU core, say, in this corner versus this corner. And so by putting the Vcore VRM on either side of the chip, you basically ensure that the lowest voltage you're going to get is right down the middle of the chip. And in theory, the difference between, the highest voltage on the outer edges should be much closer to the lowest voltage right around the center of the chip than if you had the VRM all on one side, and then, like this edge of the chip would be getting significantly lower voltage, which, when I say significantly lower, we might be talking like tens of millivolts, which doesn't sound like much, and really, like, it does only translate to like a couple tens of megahertz of clock speed difference most of the time, but like, that's unnecessary voltage you're mashing into the chip on the other side, because like the higher voltage on this side, it does increase your power draw. It doesn't improve your clock speed, because the minimum voltage is on the other side of the chip, and that's the one limiting the max clock speed. Laying out the Vcore VRM like this improves power distribution to the GPU core itself. And then we have the same thing going on with the Uncore rail, which we've got 3 phases over here and then another 3 phases over here for that. And the idea is exactly the same as with Vcore. By pushing current into the chip from both sides, you basically get better power distribution. So, Vcore is a 9-phase, Uncore is a 6-phase, and the memory VRM is, of course, a 3-phase, which I've already talked about. So then, in terms of voltage controllers, NVIDIA is using some rather nice ones. So on the front right here, we've got this chip, and that is a MP 2884. It is a 4-phase controller, and it is in charge of handling the memory VRM, because, well, that's the only number of phases that it can handle. And also you can see how there's that extra fourth phase optional for this chip to handle on the other side, if you actually had a 3090. So 4-phase controller, made by Monolithic Power Systems, goes up to 5 megahertz switching frequency, which is absolutely stupid. There's like no power stages that support that much switching frequency, at least none that I've seen. And it's also a fully digital controller, which the cool thing about this being a fully digital controller is if you figure out some way to talk to it, via software or maybe through some kind of I2C dongle connecting to the chip, you can basically get monitoring functionality for the memory VRM. You can get full control of the memory VRM, right? So you can adjust voltage, load line, switching frequency, whatever. You can adjust that because this is a fully digital controller. Now, obviously, this being an NVIDIA GPU, the software, like, there's not really any kind of software support for that. But, if you did feel like soldering your own I2C interface connection to this chip, you could. And then like the only other issue you'd run into is that there's no like public documentation for the registers of this chip, so you're not necessarily going to get very far, but I would assume that maybe Elmore from Elmore Labs will put out an update for the EVC2 that will support the MP2884, because he does already have the EVC2 already supports the MP2888, and the 8084 is just like the little brother of the 88. So anyway, this is a really high-end voltage controller from Monolithic Power Systems. Like, straight up, this is just better than what you're gonna get on basically any RTX 3080 you can currently buy. So yeah, NVIDIA is not cutting any corners with that right there. And then on the back of the card, we have our other two voltage controllers, which over here we have the biggest of voltage controllers on the card, which is the MP2888, which you might think that's an 8-phase controller, because, you know, the 4-phase controller ends in a 4, the 8-phase controller would end in an 8, but you'd be wrong, this is a 10-phase controller, which is really cool. This controller has also been used in top-end RTX 2080 Ti's, so the Kingpin Edition, I think the Galax Hall of Fame, also goes up to 5 MHz switching frequency, fully digital. It's literally the bigger brother of the MP2884, or like the really big brother of the MP2884. Because there is the smaller, bigger brother, which is the MP2886 there, which is a 6-phase controller. So see, this one follows that pattern of 6 phases, ends in 6. Also up to 5 MHz switching frequency, also fully digital. Like, you know, these are some really top-end voltage controllers from Monolithic Power Systems on this card. The Kingpin 3090 is probably going to use a very similar configuration of voltage controllers to the actual Founders Edition, because this is basically as good as it gets in terms of voltage controllers for NVIDIA cards. I also think the 2080 Ti Strix used the MP2888. Anyway, so yeah, NVIDIA is not cutting any corners on the controllers. And that's a good thing, though. In theory, the better voltage controllers might give you somewhat better transient response and better voltage regulation, but basically you'd have to check that with an oscilloscope. The thing is, there's a lot of ways to influence the transient response of a VRM that, you know, like, you might have a better controller, but then how is the controller actually configured affects it. How is the output filtering of the VRM configured? How much per phase inductance you have. So there's too many variables in that. But high-end controllers generally mean that the best configuration you can build of the VRM is going to be performing better than a similar VRM but using a weaker controller. The controllers used, very nice. The power stages used, also very nice. So for all of the VRMs on here, NVIDIA is using the MP, and this is a horrible part number, 86957 smart power stage. And this is a 70 amp smart power stage, which is not the highest current rating you can get for a smart power stage, but the funny thing is, like, technically you can get smart power stages all the way up to 90 amps. The thing is, the difference in terms of actual usable current and performance between a 70 amp part and a 90 amp part is really very small to almost non-existent. Unfortunately, with power stages, like a 40 amp part is significantly worse than a 50 amp part, but the difference between a 50 and a 60 is relatively small, and then between like a 60 and a 70, really small, and then from a 70 to a 90, it's like there's barely any difference. You're not going to see really better power stages being the big difference between the Founders Edition and then some of the later better custom cards that we're going to be seeing for the 3080 or the 3090. What we'll most likely see is that the higher end cards are still going to use similar, 70 amp smart power stages, maybe slightly higher current rating, but it's really not going to make much of a difference to the overall efficiency. But there's going to be way more phases. That's what we're probably going to see, or just more power stages in parallel to increase the current handling capacity, because, yeah, you really can't get better power stages than this. Now, the reason why these are called smart power stages is because they integrate very accurate current monitoring, also temperature monitoring, and a bunch of safety features. So that's why they're called smart instead of just regular power stages, because with a regular power stage, like, the current monitoring is optional. You don't necessarily have to have that. The temperature monitoring doesn't need to be there. So yeah, that's what makes these smart. There's a bunch of extra circuitry built into them that would otherwise have to be implemented externally with, cheaper components like, say, DRMOS components. So That's the power stages that NVIDIA is using, and what that means for the various VRMs in terms of efficiency is that the Vcore VRM, and this is really weird to draw the two arrows, is going to be outputting 1 volt with a switching frequency of, wait, I did update that, yeah, so 500 kilohertz switching frequency. Though they might still run it for they might still run the VRM at 300 kilohertz to get slightly better efficiency, but the thing is, with a lot of the smart power stages, running them at 300 or 500 kilohertz really doesn't make much of a difference, so another advantage of very high-end power stages is just like you really do need to run them at very high switching frequencies before you get like the massive efficiency penalties that come with the, like at 1 megahertz, basically every VRM gets really inefficient these days. But anyway, so 1 volt, 500 kilohertz switching frequency, which 1 volt is a little bit over what a 3080 runs as a stock voltage. Anyway, it's close enough that it doesn't make too much of a difference. So 200 amps output, this VRM is going to be producing about 17 watts of heat, which is great in terms of efficiency right there. 250 amps output, it's going to be producing about 23 watts of heat, which is still very, very good efficiency. Like basically, if the heat output is lower than the current output divided by 10, you're looking at over 90% efficiency, roughly something like that. And so, you know, over 90% is very nice. At stock, like the VRM is basically right at the peak of the efficiency curve. And then if you start overclocking, you start coming down from the peak. But, you know, like there are some VRMs where if you max them out, you're going to be hitting like 85% efficiency, at which point it's, you know, like things like water cooling the VRM start making sense. Anyway, so 250 amps, 23 watts of heat, 300 amps output, it's going to produce about 30 watts of heat, and 350 amps, and now we're, you know, really starting to dip below the peak of the efficiency curve. You're going to be looking at like 38 watts of heat, and 400 amps, it's going to produce 49 watts of heat, which, yeah, so the VRM can get very hot, especially because that heat is actually only distributed across, you know, 9 power stages. But the thing is this is a GPU where you do have like airflow blowing directly down onto the PCB. Though it also depends on the fan speed, right? Like if you have a really noise optimized design and there's not a lot of VRM heatsink, there's not that much airflow, and the VRM ends up running hotter even if it's really efficient. Whereas if it's less efficient but you throw more airflow at it, well, you can get lower temperatures. So really depends on, you know, how the cooling system here is designed. But the actual components themselves are, you know, very good, and the phase count is actually generally higher than most of the cut-down reference cards. It's also worth noting that most of the cut-down reference cards use 50 amp power stages instead of 70s, so, you know, it's not really even a contest at that point. For the Uncore VRM, we're looking also at around 1 volt output voltage, 500 kilohertz switching frequency. And because it's a 6-phase instead of a 9-phase, you know, the current handling capacity is significantly lower. So 100 amps output on, we're going to just go Uncore. So 100 amps output on the Uncore VRM, because I don't know how much power the Uncore rail pulls. You're going to be looking at about 8 watts of heat dissipation. 150 amps output, the VRM is going to be producing around 13 watts of heat. So still, you know, well into the efficiency curve. Then 200 amps, it's going to start producing about 20 watts of heat. And so generally speaking, for even a 70 amps more power stage, your efficiency peak is around 20 amps. Anyway, for 250 amps output, it's going to be producing about 29 watts of heat. So yeah, the Uncore VRM, like the thing is, I don't know how much power the Uncore actually pulls, but that is a very substantial VRM for, you know, a secondary power rail right there. And then the memory VRM, you're going to be looking at, we're just going to put that over here, 30 amps output, it's going to be producing about 3 watts of heat. 45 amps output, it's going to be producing about 4 watts of heat. And 60 amps output, about 5 watts of heat. And then 75 amps output, it's going to produce about 7 watts of heat. There is a lot of rounding going on here because it doesn't make sense to me to go down to like decimal points for the heat output of the memory VRM, which is why all of this is to the nearest watt. Anyway, So the memory VRM is also very substantial, but I don't know exactly how much power the GDDR6 memory chips pull. So again, hard to say if, like how overkill this is. Consider the fact that all of the cut down reference cards so far are using like 3 phases of 50 amp power stages for memory power. And it's just like, well, this is at least more than 30% more VRM than what you'd get on the cut down reference cards for the memory power. So yeah, the memory power delivery is also very substantial on the Founders Edition compared to some of the other 3080 options that there are. Now then, in terms of other rails we've got on the card, up here, I believe we have the PEX voltage. It might be 1.8 volts. Like, there's 2 minor voltages that are very important. You have 1.8 volts and you have PEX rail. So the PEX is for powering, like, the PCIe interface that normally sits at around 1 volt. And it's either like this inductor or this inductor. I'm not sure which. Unfortunately, don't have the card in hand. But it doesn't really matter because both of them are built with the exact same components. So you have this power stage, and then you have this other... Well, actually, these aren't even power stages. These are like fully integrated buck converters. And they really, like, those are really low current rails. They don't have to be very substantial. Like 1.8 volts is a supporting rail for the memory chips and also powers like the BIOSes on NVIDIA GPUs, and then the PEX rail only powers the PCIe interface of the GPU core. In terms of the capacitor configuration on this card, I'm also a fan of that. This is another one of the things that is actually significantly more expensive on this card compared to the reference cards, because this card has all of the capacitors on this card are SMD capacitors. And the thing with SMD capacitors is that they are significantly more expensive than their through-hole counterparts. Now, there are some benefits that you get for the increased cost. Higher density, they're low profile, you can fit them under a backplate, but the parts I care about is they get lower ESRs and lower ESLs, and especially the ESL is something. Just because of the way a SMD capacitor like this is structured, it has a much, much lower ESL than any through-hole capacitor will ever have, and that basically translates into better voltage regulation, because the capacitor has less impedance when it comes to storing and outputting energy, depending on the demands of the GPU core. So yeah, I'm a big fan of what NVIDIA has here with the output filtering on, the cut down reference cards. Most of the board partners are deciding to go with through-hole capacitors because they are way, way cheaper. In theory, it could translate into a, slightly worse GPU core overclocking in the range of, on the low end, like 10 megahertz, on the high end, like 50 megahertz, less max core clock, just because of the different capacitor configuration, because it does make a difference to the, like, it can make a very significant difference to the voltage regulation. And obviously, if you have more, level voltage delivery to the GPU core, then you can clock higher, because the main limits to your clock speed are the operating temperature and the minimum voltage being applied to the GPU core. NVIDIA could also be taking advantage of the superior performance of these capacitors to just use less of them. And then it, gets really complicated where it's like, well, there's less of these, so they might actually be performing about the same as the significantly downcosted reference cards, but I kind of doubt that, because there is a lot of capacitors here. And I'm not going to just add them all up. Also, for the input filtering, we're looking at Chemet tantalum capacitors. The output capacitors, I can't tell if they're tantalums or polymers, or like tantalum polymers or aluminum polymers, mostly because these don't look like anything I've seen before. Like, the markings are a bit different from the usual Panasonics, and so I don't know who makes those. But these are Chemets for the 12-volt input filtering, which, again, same advantages compared to through-hole capacitors on the high-voltage side. So... yeah, I'm a fan of what NVIDIA has done with their capacitor configuration here, but they've generally had like nice capacitor configurations on reference cards for a while. Yeah, that's kind of the power delivery side of things on this card. In terms of the power monitoring going on, this thing is, like most 3080s, looks like an absolute nightmare because there are so many shunt resistors, and they are being monitored by this chip right over here, which is a US 5650 from UPI Semiconductor. Unfortunately, there's no public data sheet for this chip, but from my understanding, it basically just converts the voltages measured on the various shunt resistors down to a lower voltage level that then is fed directly to the GPU core, so that, like, this chip doesn't actually do any monitoring, The core is just getting a level reduced reading of the shunt resistors from the US 5650. Shunt modding this would get kind of awkward. Also, this voltage regulator over here is probably for something like a minor rail like 5 volts, because smart power stages, they do not run on 12 volts, or actually, you can get 3.3 volt smart power stages, but I can't get a data sheet for these, so I'm just going to assume that they're normal and run on 5 volts, because normally power stages run on 5 volts. There are 3.3 volt options, but they're kind of rare. Anyway, and there's another US 5650 over here, because each of the 5650s, I believe, can only monitor like 5 or something like that shunt resistors, but the card has 1, 2, 3, 4, 5, 6, 7, 8. There was a 9th one, and I don't know where it is now. There it is. It's trying to pretend to be a capacitor, but we see you. Yeah, so there's 9 shunt resistors on this thing. And so the funny thing about having 9 shunt resistors is basically if you don't mod every single one of them, the card will know that there's something wrong with the power monitoring. So basically, if you just mod, like, you know, your primary shunt resistors, which I'm gonna guess are like these 3 right here, I hope. Again, just there's so many of them, it is impossible to tell. There's going to be a chain of shunt resistors for the PCIe slot, and there's another 2 chains coming off of the 6-pin, because the 6-pin obviously has the, 12-pin to 8-pin adapter. So, you know, in order to make sure that you don't overload the adapted 8 pins, you have to have 2 separate channels of shunt resistors to not like have independent power limits for the 2 8-pins that ultimately go into this. That's the situation with the shunt resistors on here. There is a ton of them, and you do basically have to mod all of them as far as I'm aware, because if you don't mod all of them, the card basically realizes, wait a minute, the voltage measurement indicates that one of the shunts is still measuring correctly and all the other ones aren't, so yeah, the power limit adjustment doesn't, like, it doesn't really do what you would expect it to do, and the card will still sort of weirdly hit a power limit. I ran into that issue already with a 2080 Ti, because 2080 Ti's at a first glance look like they have, I believe, 3 shunt resistors, but in fact, there's another 4 hiding around the PCB. So yeah, with the 3080, NVIDIA has really just taken up to the 9th level with 9 shunt resistors. I miss the days when NVIDIA GPUs had 3 shunts, 1 for each power input, but yeah, or 2 shunts if you had a single power connector GPU, right? Not this horrible mess right here. And the reason why we have all of these shunt resistors is because NVIDIA actually uses them for shuffling around where each VRM is pulling power from to basically balance the power draw across all of the power inputs. Where AMD basically just has a total GPU core power limit, and then they don't actually have a power limit for things like the memory a lot of the time, or the memory controller, because that would be too expensive to implement. NVIDIA actually straight up has a power limit, like 8-pin 1 power limit, 8-pin 2 power limit, PCIe slot power limit, and then when you hit the power limit of 8-pin 1, you know, NVIDIA has the option to basically go like, okay, so we're going to pull a little bit more, like skew more of the current draw to 8-pin 2 to reduce load on 8-pin 1. Or alternatively, you could just not have a power limit system like that and, you know, just hope that the power, like each of the 8 pins is relatively balanced on its own, which is basically what all AMD GPUs do, because they don't have all of this extra circuitry for that. Like, I'm not a fan of this because it just makes the GPU more complicated for no good reason. The thing is, like, 8-pin power connectors can handle significantly more current than they are rated for. Like, way more than they're rated for. So even like the new 12-pin, which NVIDIA is like, oh, it supports more power than dual 8-pins. Yeah, it supports more power than dual 8-pins according to PCIe spec, but that's because the PCIe spec underrates the 8-pin by like 50%. So, unnecessary. When have NVIDIA GPUs done anything because it was actually necessary instead of just like, but it looks more complicated? Because it is. Thing is, you can't get away from all of the power balancing stuff. Like, this is just a requirement on all of the 3080s that I've seen so far, so You know, it's just like if you're thinking of shunt power modding one of these, you're gonna always be going through the same pains of there is 9 shunt resistors. Have fun with that, regardless of which model you buy so far. Or you could just wait for like a Kingpin edition or something, which will hopefully come with a BIOS that removes all power limits eventually. Though they're not going to make one of those for the 3080, I guess. So yeah, if you want a 3080 with no power limits, that might get kind of awkward. Out of the PCBs available right now, this is certainly not the worst option, though it does not have the highest available power limit. I do believe the max power limit on this PCB is 370 watts, unless you start, messing with all of the shunt resistors. So yeah, there. That is actually it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support us here at Gamers Nexus, we've got a Patreon. There's a link down in the description. And then there's also store.gamersnexus.net, where you can pick up things like the Gamers Nexus mod mat, which is what the 3080 here is sitting on. That's mod mat behind the card. So yeah, that's it for the video. Thanks for watching, and goodbye.